Now let's solve some very good undetermined coefficients problems. So we have a differential equation y double prime plus y prime minus 2y equals to 2t, and we are given these initial conditions. So how can we approach this problem? So first of all, what we want to do is use the characteristic equation to use the homogeneous solution. Okay, so we're gonna write the homogeneous solution r squared plus r minus 2 equals to 0. This is the characteristic equation of the homogeneous part. And factoring out this will give us r plus 2 multiplied with r minus 1. Okay, so this will give us r1 equals to negative 2 and r2 equals to 1. So we are going to have a solution. Since these are distinct real roots, our solution will be c1 e to the t plus c2 e to the minus 2t. And this is called your homogeneous solution. Okay, this solution doesn't work for the differential equation because this only would work for the homogeneous version of this differential equation. Or this is an unhomogeneous differential equation. It's not homogeneous, so you cannot use it. But what we will do is use the homogeneous solution to build the general solution. When we add it to the particular solution, that's going to come from the undetermined coefficients. But before we do that, we have to start with getting the fundamental set of solutions. Our fundamental set of solutions, yf, is going to be e to the t and e to the minus 2t. It's because we just ignore the constant terms and get the function piece for the builder functions that build the homogeneous solution. So once we have these main pieces, this will be our fundamental set of solutions. And once we get the y particular guess, it should be linearly independent with the fundamental set of solutions. If it's not, then we're going to keep multiplying with t until we make it to be linearly independent, because that's the main rule, the main theory of having undetermined coefficients method. So for this problem, we have a first order polynomial, first degree polynomial. So our polynomial will give us a y particular value, and our y particular will be at plus b. This is an example polynomial with first power, the first power polynomial. These a and b could be anything, and this is going to be our y particular. Now if we check with the fundamental set of solutions if it's linearly independent or not, we can clearly see that we don't have a e to the t or e to the minus 2t in this part. So this means that we are linearly independent. If you're not sure about the linear independence, you're free to try it out using the Wronskian, and the Wronskian will help you understand. If we have a non-zero Wronskian, that will show us linear independence, which we would have if we did that, and this will ultimately prove us that we are linearly independent. So we don't have to do that, since clearly these are linearly independent. So we can just go ahead and use this to build our differential equation. So our first derivative of yp prime is going to be a, and our second derivative is going to be 0. So if we plug this in a differential equation, we will have 0 plus a minus 2at minus 2b. Okay, and this will be equal to 2t ultimately. So we don't have any constant terms. However, our minus 2a is the coefficient in front of t, so this gives us that a is actually equal to minus 1. It's because the only way to make this minus 2at true to 2t is making this a to be negative 1. So a will be negative 1, and we will have a negative 1 minus 2b, and this must be equal to 0 since we have no constant terms. And that will give us b equals to negative 1 over 2, basically. So in this case, our y particular would be negative t minus 1 over 2 equals to our particular solution, guys. And to build the general solution, we will have y general equals to the yh plus yp. So now let's build the general solution. So our y general is going to be c1e to the t plus c2e to the minus 2t minus t minus 1 over 2. And this is our general solution for this differential equation. However, we are given these initial conditions, so we want to find a specific curve to satisfy this differential equation. Now, using these points, we can plug 0 for t and 0 for y to get the first initial condition, and that will be 0 equals to c1 plus c2 minus 0. I'm not going to write minus 0, minus 1 over 2. And this will generate us an equation c1 plus c2 equals to 1 over 2, which is going to be helpful because we're going to need another equation, y prime of 0. So if we get y prime will be c1e to the t. This is a equal sign. Y prime equals to c1e to the t plus c2 minus 2t c2e to the minus 2t minus 1. And this is y prime. And if we plug 0 for t and 1 for y, we will have 1 equals to c1 minus 1. So c1 is actually equal to 2. So since c1 is equal to 2, from this equation we know that c1 must be negative 3 over 2. So given that we know what c1 and c2 is, now we can write the general solution for this specific curve, negative 3 over 2 e to the t plus c2 was 2, so we will have 2e to the minus 2t minus t minus 1 over 2, and this will be the solution of our differential equation. Now let's work on this example problem. Y double prime minus 2y prime plus y equals to e to the t, and we are given these initial conditions. So the first thing we want to do is set up the characteristic equation to solve for y homogeneous, and this will be the square of r minus 1 equal to 0. r1 comma 2 is going to be 1. This gives us our equal real root solution, e to the t plus c2t e to the t. Now we have the y homogeneous solution, and now we want to find the particular solution, but before that we want to see what the fundamental set of solutions are. So we will have e to the t and te to the t here. And now let's, if we want to make a guess, our guess would be ae to the t. However, this is linearly dependent with the fundamental set of solutions, so we will be multiplying with t, so ate to the t. However, this is still contradictory to fundamental set of solutions, as you can see the second term here. So you would multiply with t again, so at squared e to the t. And now this works for our particular solution because there's no linear dependence here. So if we go ahead and plug that, our first derivative would be 2at e to the t, and our second plus at squared e to the t, and our second derivative will be 2ae to the t plus 2at e to the t plus 2at e to the t plus at squared e to the t. And if we further simplify, yp double prime equals to 2ae to the t plus 4at e to the t plus at squared e to the t. Our differential equation was y double prime minus 2y prime plus y, so if we go ahead and write that, 2a e to the t plus 4at e to the t plus at squared e to the t minus 2y prime, so minus, we will be subtracting 2y prime, so this will be 4at e to the t minus 2at squared e to the t Okay, now we have y double prime minus 2y prime, and now we want to add a y, because in the differential equation we had y double prime minus 2y prime plus y equals to e to the t. So if we add one y, we will add at squared e to the t, and that was equal to e to the t. So at squared e to the t, we have 2. So we will write that 2at squared e to the t. And we subtract 2at squared e to the t too, so we can just get rid of that. We are subtracting these two, so we are left with 2a e to the t equals e to the t. This gives us a equal to 1 over 2 plus 1 over 2. So y particular will be 1 over 2 t squared e to the t. Okay, once you find your y particular solution, it becomes really easy to find y general, and that's yh plus yp. And in this case, our solution, our complementary, our homogeneous solution was c1 e to the t plus c2 e to the t, t to the t. So we will have just like this, plus 1 over 2 t squared e to the t. And now plugging the initial values will give us the c values. So y0 is 1 and y prime of 0 is 1. So we will be able to find those. So if we plug 0 in the general solution, we will have c1 because e to the 0 is 0 plus 0 because c2t is, that's why it's going to be 0, and we have a 0 here, so c1 is going to be 1 from this first equation. Now let's find c2. Taking the first derivative, I'm just going to update this solution. It's going to be c, instead of c1 we're going to have just 1 here, so 1 e to the t. Okay, so now we can find the first derivative, and that's going to be e to the t plus c2 e to the t plus c2t e to the t plus 2t e to the t plus t squared e to the t. And now if we plug 0, we will cancel these terms. This will be 1 plus c2 equals to 1. This means c2 is 0. So c1 is 1 and c2 is 0. So our solution for this differential equation will be y general equals to e to the t plus 1/2 plus t squared e to the t. Now let's work on this problem. We have a differential equation and a particular solution. It's non-homogeneous, so we will start with forming the characteristic equation equal to 0. And this will give us our roots, and this will be r minus 4 multiplied with r plus 2. R root 1 is 4, and r root 2 is negative 2. Since we have distinct real roots, our y homogeneous will be c1 e to the 4t plus c2 e to the minus 2t. Okay, now our guess will be, before that, our fundamental set of solutions is e to the minus, e to the 4t, comma, e to the minus 2t. Okay, and our guess for yp will be a e to the minus 5t, and this doesn't contradict the yf, the fundamental set of solutions, do work out perfectly. So we can go ahead and use this y particular. So we're going to get the first derivative is going to be negative 5a e to the minus 5t, and the second derivative will be 25a e to the minus 5t. Now let's go ahead and plug that into the differential equation. 25a e to the minus 5t minus 2 times y prime. So it will be minus 2 times minus 5, plus, which means it's plus 10. A e to the minus 5t minus 8 times yp, which is a e to the minus 5t, equals to 2 e to the minus 5t. Okay? So we will be reducing this, and this will have 2ae to the minus 5t, and we have 25 there, so we will have 27 a to the minus 5t equals to 2e to the minus 5t from the given equation. And this means that if we can divide both sides by e to the minus 5t, a will be equal to 2 over 27. Okay, so we can write yp as 2 over 27 e to the minus 5t. So our general solution will be y general c1 e to the 4t plus c2 e to the minus 2t plus 2 over 27 e to the minus 5t. And our initial conditions were both y0 equals 1 and y prime of 0 equals to 1. So if we have y0, this means that c1 plus c2 plus 2 over 27 equals to 1, because this exponential term will generate 1. So c1 plus c2 equals to 25 over 27 from the first equation. And now if we get the first derivative, our first derivative will be 4c1e to the 4t minus 2c2e to the minus 2t minus 10 over 27 e to the minus 5t. Okay, and since we have this, let's go ahead and plug 0 for t, so we will have 0 will be 4c1 minus 2c2 minus 10 over 27 equals to 1. So this means that 4c1 minus 2c2 equals to 17 over 27. Actually 37, my bad. 37 over 27. Okay, and our first equation gave us c1 plus c2 equals to 25 over 27. So now let's multiply the second equation by 2. We will have 4c1 minus 2c2 equals to 37 over 27, and this will be 2c1 plus 2c2 equals to 50 over 27. And if we add these equations together, we will have 6c1 equals to 87 over 27, because we will be getting rid of c2, so this will help us solve for c1, and c1 will be 87 over 27 times 6 is 42, 12, 162. Okay, and c2 will be 25 over 27 minus 87 over 162, and you can just leave it. The fractions are a little bit complicated, it's okay. And now if we go ahead and plug that into our solution, c1 was 87 over 162, 87 over 162 e to the 4t plus c2, which is 25 over 27 minus 87 over 162. You will have better fractions in your exams, guys. Don't worry about the fractions. As long as you can understand the idea of homogeneous, of undetermined coefficients, this lecture would be done more than its purpose. Okay? So this is your y general solution for this c value.